Hello everyone, my name is Ravinder. Today I am going to discuss about the driving sustainability, environmental benefits of our efficient power moding in vehicle software. So today I am going to little bit about the how the vehicles are using the power, both electrical and conventional vehicles. Hope you will enjoy the content. Let's get started. Start with me. I'm one of the top automotive industry, General Motors, as an advanced infotainment system integration engineer. I was working in past 12 years and in the same automotive field, but a different backgrounds. Embedded software engineer and then firmware engineer and then integration engineer, infotainment engineer, different roles, but all are in the automotive industry. Let's get into the details and then let's get into the power management system. And yeah, sure. First thing, let's talk about the basic things. In vehicle means there are so many ECUs. ECUs means electronics control unit. So each electronic control unit manages particular function. So let's suppose body control module. It operates like it to maintain the lighting and then brake and then the body related things. It controls those things. And then there are around like 16 to 32 ECs in a particular car, depends upon the vehicle manufacturer. Each ECU is operating differently. Like one ECU is using less power, one like another ECUs need constant required power to operate it or perform the actions. In order to reduce the power, and then we need to minimize those power consumption each ECU. And we will talk about more into the coming slides, but yeah, that is the basic thing. And then the battery life cycle. So inefficient power management leads to a shorter battery life. You like when you charge the vehicle, it was like 280 miles, but in the next day, without driving your car, but your battery got shorter to a 270 next day because of you don't know what happens with the difference because of there are so many operations running on the background. So these are the ECUs consume the power and then run the background things. And then there is another thing is different power state we are going to discuss in the propulsion and then run and G and then different power modes we are going to talk about, and then how the different ECs, electronic control units, are using when you are when the vehicle is in sleep. So we will get into these details. These are the basic things. We'll get more into depth into the things. Yeah. So how the power moding works. So the first question is how the power moding works. So power moding means there are different kinds of power moding. So whether power is using the battery when you're driving, that is power used by your regular usage. And then the vehicle is sleep when you are parked in your garage, and then vehicle is no longer using, but still using the power. That's the problem with the electronic control units. So they are constantly require power to operate internally. So that's where the power moding has in a different kinds. Like it's operated in a sleep mode, operated in a run mode, operated in a propulsion mode. Propulsion means when you are driving, that is the propulsion. So there are a couple of things. So environmental sensing and then real-time analysis and dynamic adjustment and then continuous optimization. So these are the 4 steps we need to discuss. First thing is environmental sensing. Vehicle systems monitor usage patterns, driver behavior, and then environmental conditions. Based on that one, the power module got adjusted. When you are like drive the vehicle too too speed, too accelerated too frequently, then the power consumption gonna be high, and then based on your driving behavior, the power consumption got changed. And then there is an real time analysis. How your vehicle is operated, different power states, each component, which each component using the how much power in the real time when you got the data from the vehicle, and then you will analyze. That is the second step. And then third step is dynamic adjustment. Once you got the data, once you driver behavior and then environment condition of the vehicle, and then you got any real time data of that power modeling of that vehicle, and then you can adjust the ECU or ECU power between the two different ECUs, are like how much power using when the vehicle is asleep. So you can adjust based on that one. And then the fourth step is continuous optimization. Once you are done with that, all the real-time analysis and dynamic adjustment, then the last step is how to reduce your power, maximize the efficiency. So that is the fourth step. We need to be work on that one. So let's talk about the quantifiable benefits of electrical vehicles. So nowadays, so many vehicles using the battery power. Some manufacturers are like, hey, we are like 500 miles for full charge. But that doesn't mean that it's 500 miles. Drive straight. Because of there are so many functions running on the back. Let's suppose HVAC, the AC and the heat. So when you are turning on the AC, the battery gonna be reduced to 5%, 2% based on your drive behavior. So let's talk about the quantifiable benefits. So first thing is energy efficiency gain. Overall consumption of the power, how the power you have in 100% discharge. Then energy efficiency gain means for power consumption is going with your behavior, driving behavior. And then range extension, increase the driving range in when you are driving in a highway or without brakes or with brakes, or you are sudden increase the speed. So that is also your power management adjusted. And then third one is the battery life. Like most of the manufacturers are suggesting 80% of charge, because of if you charge 100% every time, the battery gonna be depleted. And then so the power modding is you want to maximize maximum extension of battery life. That's the goal of this one. And then the driver gonna be enjoy and then long drives. So that's the basic thing to of the power modding model. So let's talk about the impact on the conventional vehicle. So in the previous slide, we were talking about the electrical vehicles, and then now we are talking about the conventional vehicles, how the conventional vehicles are independent of the battery. So when you fill the gas, and then you need to be care about the fuel consumption, and then CO2 emissions, and then the component lifespan, and then maintenance interface. So these are the things you need to be considered on the conventional vehicles. In the fuel consumption, reduce a reduction of 2 to 4% and saves up to 110 kg of CO2 annually per vehicle. So with the power consumption, because of if you are using the too much of power modding means too much of power in the vehicle. So you need to burn the gas high. So that is the other thing. And then environmental impact. So what are the environmental benefits when you are working on the power modding model and like power modding, reduce the power modding in the vehicle? So the direct emission reduction, like the first thing is you reduce the fuel consumption. That is the first thing. And then more efficient operations in the vehicle. And then extended component life cycles. You reduce the battery, you reduce the power, and then increase the battery lifespan. And then the battery gonna be sufficient for your needs. And then manufacturing footprint, fewer replacement parts needed throughout the vehicle life, because of you are reducing the less power of the vehicle, and then vehicle is more sufficient and then efficiently run toward your vehicle life. And then resource consumption, lower demand of the raw materials and in battery production. So that you are ultimately saving the battery and as well as the battery raw materials. So that is the another benefit of this power modding. So implementation. In the previous slides, you are talking about the how the battery EVs are doing, and then conventional vehicles are doing, and then now talking about the implementation. How we are going to implement this power modding with the efficient power modding model. So first thing is vehicle preparation. So software updates are updates installed across around 500 test fleet vehicles. So that is test fleet vehicles, and then ECU firmware upgrades. So these are the different power consumption when the vehicle is asleep. When there is an OTA update, over the air update from the manufacturer, but you don't want to install right away when you're driving, but the vehicle needs That is a critical update. You need to update it as soon as possible. Then the only way is doing the vehicle C. Vehicle C, the automatically trigger that update and then it automatically update. And then the second one is ECU firmware upgrades. And the ECU needs a critical update for your functionality, for your safety, or for infotainment changes or anything. Any major changes, the manufacturer send their update to upgrade your firmware. That needs to be a power as well, like when the vehicle is key. And then the power management protocol integration. So that is the other one. The third one, when the power is consumption by the vehicle when vehicle is in sleep. So we need to monitor that one. So that is another one. And then algorithm optimization based on the fleet data, and then driving pattern recognition and environmental adoption. So these are the implementation of refinement of the power modeling. And then the monitoring period, how long you're going to be monitor this power modeling. Let's suppose collect the data for 12 months of data, and then check the data, which ECUs are consuming more power. And then after that, you get the data, and then you get the regular checks and everything, and then you need to verify the data, the comprehensive performance analysis, and then energy consumption patterns. You get all the components, and then you'll find out like what need to be improved, what ECU consumed more power, which way we need to reduce that power. That is this case study. The case study is completed, then the technical implementation challenges. So once you got the data, and then you have everything what you're supposed to do. So first thing is system integration complexity. So in the first slide we were talking about, so the vehicle means there are so many number of ECUs. Each ECU perform different operations. So each ECU communicated with a different ECUs as well. And then so creating a unified power modeling model is very difficult because of one ECU consume less power, another ECU consume more power, because they depends upon their usage, and then class platform compatibility. Whether the ECS is need to be interacted with outside of the one. Let's suppose telecommunication model needs to be interacted with current servers, and like an AT&T or Verizon, and then each ECU has a different suppliers or like different mechanisms. So we need to coordinate that. That is the first one. And then safety critical system. So some of the in the safety critical system, when the vehicle is theft, so you need to be that particular ECU need to be awake during the safety critical operations, or when the accident happens. So when somebody open your door when you are not there. So those kind of situations, the particular ECU needs to be very active, and then need to be trigger the safety alarms. And then as well as you need to be ISO 26262 function safety standard must be maintained. So these are the functions you need to be maintained. And then legacy as hardware constraints. Older vehicle platforms may lack the necessary hardware to support and advanced power states, and retrofitting capabilities requires careful hardware software co-design may increase the initial implementation costs. So these are the technical challenges. So we were facing standards and industry collaboration. So this is another thing. So there are the functional safety ISO requirement, that is a 26262, establish the safety requirements for both electrical and conventional vehicles in the automobile, ensuring the power modeling transition don't compromise the critical functions. This we were discussing, like when the vehicle is theft, when the vehicle is not located, like somebody stole the vehicle, the particular ECU need to be active each and every time when the vehicle is asleep. That is the 26262 function safety requirement says. And then another thing is authors partnership. Standardizes the software architecture for the ECU power management. Now, when you designing the ECU, you need to be care about how the ECUs are functioning, and then how the ECU power molding are designing that need to be discussed earlier. And then you need to be enabling the intro between the different manufacturers and suppliers. Manufacturers and suppliers need to be a partnership to understand the requirements of that particular power module, and then as well as the how this whether you need to be compromised or not based on the functions they perform that particular ECU. And then the another one is cybersecurity standards. So cybersecurity is unauthorized control of that vehicle or prevent unauthorized usage of that vehicle or the security concern. So those are the things you need to be aware. You need to be active every time. So those are the cybersecurity requirements. And then you need to be every time must be on. And then cross-industry working groups, collaborative efforts between the automotive and semiconductor and software industries to develop a next generation forward, next generation management solution. These are the one we need to be focused on. So these are the different kind of industry collaboration things we are working on that. And then future opportunities and directions. So current power molding model, discrete power states based on the predefined conditions. And then the next is going to be AI-driven optimization. AI looking into that power management thing, and then see that okay, this ECU consume more power. Why? If this is necessary, yes. If it is necessary, yes, you can use that power. If it is not necessary, then stop that ECU to use the power and then shut down that ECU. This is the next level of AI-driven optimization. And then V2X, vehicle to other, vehicle to charging, vehicle to vehicle. So these are the vehicle to X integration, power management control with the infrastructure of other vehicles. So these are the next level. And then distributed intelligence. So autonomous power decisions at individual or component level. Whether the ECU decide itself whether I need to be wake up or sleep or like you don't use the power. Is this necessary operation to perform right now? Yes or no? Based on the decision it autonomously taking the decision by the ECU or based on your program, it automatically change the power model condition. So the final key takeaways and next steps. So the first thing is significant environmental impact. So when the power management is properly organized or properly maintained in the software level, vehicle software level, so you need to be the vehicle is environmentally benefited, and then a power modem delivers measurable emissions reductions is a resource conservation across both electrical and conventional platform with a potential and exponential impact when they're applied at scale. You are produce millions of vehicles each year, but you need to be more careful about the power model because of each vehicle consumption, power consumption will impact so many emissions. So that is the first step. And then a software-driven solution. So that's where we are working on that. Unlike hardware-based efficiency improvements, power modeling leverages a software innovation that can be deployed rapidly across the existing vehicle platforms through updates and providing immediate sustainable benefits, like whether the particular software particularly sees consumption more. So why it is more, then we need to be software that capable that it is necessary use that particular operation. Yes, if it is necessary, then use that power. Otherwise, just stop it and then just don't use the power, and then are like low power mode, just minimum power using. So that's the software development solution. And then industry standardizations. And then advanced standardized approach to power management will accelerate the adoption of and maximum environmental benefits across all the automotive industries. Require a continuing collaboration between the manufacturers, suppliers, and then the regulatory bodies. So these are the steps we need to take care. Otherwise, if the too much power consumption by the vehicle, then it's gonna be replace the battery, and then there are so many disadvantages. So that's why the power management is a key component for the vehicle manufacturers. Hope you all enjoyed this presentation. Thank you so much. If you have any questions, reach out to me over the email or LinkedIn. Thank you so much.